So good morning, ladies and gentlemen, and very happy to second what Bill said about the organisation. Thank the organising committee and for the excellent organisation and the brilliant welcome that they've extended to us. So committee 2, and the remit is as shown here, to develop reference models and data, including dose coefficients. And we have a large programme of work currently, which is centred around the replacement of current dose coefficients with publication 103 compliant dose coefficients. So that is essentially values of effective dose for internal and external exposures. Effective dose being the primary quantity, of course, but also values of equivalent dose to organs and tissues. And to do that, we have a highly competent international team, and within that, I'm very pleased to say that we have our man from Korea, Professor Chan Kim. And here, this is the this isn't the official photograph from yesterday. This is courtesy of John Boyce, but to show you, and it includes 2 previous chairmen of Committee 2, Hans Menzel, who continues as a member of the main commission and is also chairman of ICRU, and Professor Christian Streffer, who is also chaired Committee 2 and is now emeritus member of the main commission. So, task groups of Committee 2 currently have 5 task groups, and if I start from the bottom there, we have a task group that develops the computational phantoms in which radiation doses are calculated, and that is obviously responsible for the radiation transport calculations as well. That's led by Wes Bolsch. Moving up, the next one is task group 95, which is responsible for the replacement of all the internal dose coefficients for workers and members of the public. Chaired by Francois Paquet. Next, task group 90, for the first time, this is looking at external dose coefficients for environmental exposures. So, important, for example, after an emergency, looking at doses to members of the public, including children. Task group 79 on effective dose. I'll be talking about that later in the week, and I should say you will also be hearing quite a bit more from Francois Paquet, Wes Bolsch on aspects of the work. So Wednesday afternoon there's a dedicated session on dosimetry. And then the last and top of this list is an established task group, first of all, of Committee 3, which has more recently become a joint task group of Committee 2 and Committee 3, and is now jointly chaired by Dietmar Noschke from Committee 2 and an emeritus member of Committee 3, Soren Madsen. So, because the replacement of the dose coefficients with 103 compliant dose coefficients is taking quite some time because of the complexity of the work involved. Among the recent publications that we've issued is publication 119, which was a requested compendium of dose coefficients for both external and internal exposures based on publication 60 methodology, radiation and tissue weighting factors and so on. So those are the current dose coefficients until replaced. And then in parallel with that, a similar compendium has been produced for current information on radiopharmaceuticals, publication 128. And then if we go on, here is quite a substantial list of forthcoming publications. Some are imminent, others will take some time to appear. So a number of publications on the phantoms, and a number of publications on the internal dose coefficients, replacing the dose coefficients for workers and then members of the public. And as I mentioned, for the first time, external dose coefficients for members of the public, and this publication to deal with the appropriate use of effective dose. So just a bit from me about aspects of this work, and as I say, Wednesday afternoon, more details. But in terms of phantom development, the current dose coefficients, as compiled in 1119, and indeed the radiopharmaceutical compilation, are based on stylized representations of the human body, mathematical representations, as in that top compartment. But the decision was made in the development of the 2007 recommendations to move to more realistic phantoms of the human body based on medical imaging. And so moving on to the more realistic as we move down this chart, and essentially voxelized representations based on real images of humans, but adjusted to the sizes and shapes of ICRP reference male and female. So the adult phantoms have been issued, and that was that publication 110 in 2009. All the calculations associated with those phantoms have only very recently been completed in terms of the internal source target radiation transport calculations. But of course, now we have male and female phantoms. Another additional complexity is the calculation separately of organ and tissue doses for males and females, and then the averaging of those in the calculation of effective dose. So just a few pictures and the details Wes Bolsh will talk about on Wednesday. This is the series that have been adopted and will provide the reference phantoms for children. And we will also, at the midline here, have a reference set of phantoms for the human fetus and the associated pregnant female. And then an important development within Committee 2 is moving on to the next stage of sophistication in terms of phantom development. And this is work that is being done here by Chan Kim. And this is moving away from voxelization of phantoms and increasing the resolution that the phantom is capable of by calculating radiation transport in a non-voxelized model of the human body. But again, Chan will be talking about that in detail on Wednesday, but that allows all radiation transport to be done within the phantom. Currently, some of the detailed calculations of doses within tissues and organs have to be done separately outside the phantom. So moving on to a little bit about the task group 95 responsible for replacing the internal dose coefficients. The first job is replacing the worker dose coefficients. There's a number of parts to this enterprise. And for the first time, this will bring together both the dose coefficients and the bioassay data that is required when measurements are being made to assess dose to workers. So the introduction is ready to be issued. There's publication 130, and then there's these parts, as you show. The text of these publications for part 2, 3 and 4 is well developed. The calculations are moving on quite rapidly, particularly for parts 2 and 3, and 4 should be it should be possible to complete those into the beginning of next year as well. For the first time, radon is included in the list here. It's in part 3, as shown there. Now, as well as the new dosimetry, a lot of effort is going into improving the biokinetic models, and I'm just giving one example here, but throughout, looking at each of these elements, a detailed review has been undertaken to look at whether improvements need to be made on the basis of improved information. And the general trend is to make these models physiologically realistic, and of course then the excretion is modelled explicitly so that they can be used for bioassay as well as the calculation of dose coefficients. And this is just the example showing that this is a movement to a more physiologically realistic model for iodine. And this is just an illustration of the sorts of information that will be included in the printed document. So the printed document will have the effective or committed effective dose coefficients in printed form for a number of inhaled chemical forms depending on the element and the radionuclides, and ingested materials. All the additional information for different aerosol sizes, so this is just for 5 micron aerosol AMAD, other particle sizes and the equivalent dose coefficients will be made available electronically on the publisher's website. So there's a mass of additional data. Also, in the printed form, but backed up by additional data in electronic form, will be the bioassay functions for the interpretation of bioassay measurements. So here's an example for cobalt. Just a few words about radon, as I say, included for the first time in terms of the calculation of dose coefficients using dosimetric models, biokinetic dosimetric models. This is a good example of the committees coming together and working on a topic. So these are 2 publications that have been issued since the 2007 recommendations. The first, publication 115, Bill already mentioned, the Committee 1 task group led by Margot Tiermarsh on lung cancer risk from radon. And on the basis of that, the proposal was that the epidemiology indicated that we should increase the nominal risk coefficient for radon-induced lung cancer by about a factor of 2. And that was included, then endorsed by ICRP in a statement on radon. But in that same statement, ICRP indicated its intention to move to dosimetric calculations, and hence that's why we're including it, of course, in the OIR series. Committee 2 have been involved in each of these publications. The second is looking at how radon is dealt with within the system of protection. So here is photographic evidence of the committees working together, a group of Committee 1, Committee 2, Committee 4 members talking about the way in which we deal with the available evidence and describe the newly calculated dose coefficients. So, as usual, radon is unique among the radionuclides we deal with because we have this considerable body of information from the epidemiology. And the epidemiology can be used to provide us with a value of dose per unit exposure. So as well as the dosimetric approach to calculating doses from radon, we can also calculate it directly from the epidemiology. And the consideration of this little group and in discussions within the main commission and within committees was that we should take into account both these sources of information. And on the basis of that, the proposal which has been endorsed by ICRP is that for most circumstances of exposure to inhaled radon-222 and its progeny, we use a single dose coefficient of 12 millisieverts per working level month. But the OIR3 document will provide the data for alternative calculations should that be seen as necessary under particular circumstances of exposure. And just for information on this slide, that dose coefficient means that the upper reference level, which ICRP has adopted, of 300 becquerels per meter cubed for homes, and also applied in general to workplaces, as discussed in publication 126, corresponds to a dose of the order of 10 millisieverts. Okay, so I think this is a topic for a future symposium. The work that is ongoing at the moment, led by Nina Patusians, on dose coefficients for external environmental exposures, different types of environmental exposure, considering children as well as adults. And likewise with radiopharmaceuticals, an important source of medical exposure. Effective dose I'll be talking about on Wednesday, and I leave you with a final slide. This is an extensive program of work. It is complex and it is taking some time to complete all these dose calculations, but the work is essentially groundbreaking and world-leading. Thank you.